Can someone on Zoom confirm that they can hear me? Great. Okay, welcome back to the machine learning lecture. First, before we start with the lecture, somebody asked about assignment number 5 and the grading. The grading has started. The tutors are doing the best they can. If you want to double check whether you can take the exam, I guess you should be able to just reverse engineer what is the smallest number of points you need on the 6th assignment in order to be able to get to the exam. So unfortunately, we just are not able to speed it up. So it has already started. The tutors are doing the best they can. I don't want to make any promises, but it should be roughly within a week. Let's see. Okay, so today we're talking about support vector machines, which is back on the topic of classification. And these are special kinds of models that, as we'll see, introduce what is called large margin classifiers. Before we can start with support vector machines, first let's review some knowledge from geometry. So the object that we'll care about here are called hyperplanes, which are in some p-dimensional vector space. Essentially, a linear hyperplane is a p-1 dimensional subspace, right? So if you think of the 2D space, then the hyperplane is just a line. And this is exactly what is illustrated in this figure, where we have 2D space, x1, x2 axis, and we show the line, or in higher dimensions, the hyperplane, which corresponds to the function 1 plus 2x1 plus 3x2 equals 0. So exactly this line that we're seeing over here. And the special thing about hyperplanes is that they divide the space into 2 regions. So one region is where the points are all greater than the hyperplane. So this equation holds. So essentially the same equation for the line, but now instead of equals 0, we have bigger than 0. And then the opposite side, the half space, where all of the points lie below the hyperplane. So the same thing holds in 3D space. In 3D space, the hyperplane is just a plane. We have points above it, points below it, and so on in higher dimensional space. One thing to keep in mind here in terms of terminology, we have a linear and an affine hyperplane, and these are almost the same, except that the affine hyperplane also has this additional bias term, the B0. But other than that, essentially, hyperplanes are defined as a set of weights, a set of coefficients, B1 to BP, which are multiplied with the input. And yes, the hyperplane, by definition, is all those points that lie on the hyperplane equals 0. Another thing that we know about hyperplanes is that we can define them via their normal vector. And their normal vector is essentially determined by the coefficients in front of the variables, so the coefficients in terms of in front of x1 and x2 give us the coordinates of the normal vector, that is the vector that's perpendicular to this hyperplane. Or in 2D, the vector that has 90-degree angle with this line. And often what we do is, because here we more care about the direction is the only thing that determines where the hyperplane is and how it divides the space. We care more about the unit normal vector, and we do this by simply normalizing the vector by its norm. And when we consider the unit vector, these two additional lines or hyperplanes appear, and this is exactly where the function equals 1. So this is where all of the points that lie on this line satisfy such that if you plug them into this equation, they equal 0, and all of the points that go on this line or this line, if you plug them into the equation, you get 1 and minus 1. Right, so this is just some definitions to recall how planes, hyperplanes work in high-dimensional space. Now, let's get to our classification setting. So as before, we have a data set of two classes, the blue and the red dots. And in this case, the data set is separable, which means there exists a hyperplane that can separate the data. And not only that, but in this example, you see there are many different possible hyperplanes or lines that separate the data. So we have this one, this one, this one, but also many other, in fact, infinitely many lines that will separate these two classes. So another question is, which of these lines is the best possible line, right? If we have so many, how do we choose one of them? And if you look at the slide here, we have three possible choices. Which of these three choices would you say is the best? Just intuitively. Yes? Would you say, so this one or this one? Which one? This one? This one. Yes. So what makes you say that? Exactly. So just to rephrase that, so we have these three choices. This first hyperplane is very close to a blue data point. This other hyperplane is very close to a red data point. So now imagine that the data was slightly more noisy than this, or a new test data point comes in, it could easily be on this other side of the hyperplane, which means it will be misclassified. While if we choose the hyperplane in the middle, we give ourselves a little bit of slack. So there's some room between the hyperplane and the points on the blue side and the points on the red side. And this additional room makes sure essentially that we don't overfit, that if new data points come in, it's more likely that they'll be on the correct side of the hyperplane. Right, so just as before, we have our data matrix of p-dimensional data points. We stack this data matrix into these data vectors. We stack them into a data matrix, and we're concerning ourselves with the binary classification into 1 and minus 1. And we'll see exactly how to do this with hyperplanes. So let's just use what we defined one slide before. The hyperplane is all of the points that lie on the hyperplane. When you plug them into the equation, you get 0. Everything that's above gets 1. Everything that's below gets minus 1. So let's exactly use this to do classification. So we'll plug the data point into this equation, into this linear equation, and look at its sign. If its sign is minus 1, it's class minus 1. Otherwise, it's class 1. Or visually, what this corresponds to, we get a new data point and simply check, is it above or is it below? And another thing which is interesting here, which can tell us some additional information rather than just what is the prediction for this node or for this instance, is the distance. So in some sense, we can say the further away a data point is from the hyperplane, the more sure we can be, the higher our confidence that this data point is correctly classified. So now let's try to formalize this idea of finding a hyperplane that separates the two classes as best as possible. And essentially, one way to think about this is we want to maximize the distance of the closest point, the closest training data point to the hyperplane. And if distance is as high as possible, that means we have the best possible hyperplane. So this is how this looks like. We have our hyperplane. We extend it onto both sides until we hit a data point from class 1 and a data point from class 2. And this distance is called the margin. So this is the maximum possible distance we can get such that all of the data points are still correctly classified, plus there is no way to rotate or to change this line such that there's larger distances between these two classes. So one question here would be, okay, we have our hyperplane and we have these two lines which essentially touch the closest blue and closest red. Where would we place our actual classifier? Well, the best idea is to just place it in the middle, because then we have equal slack to the blue and equal slack to the red, because there's no reason essentially to prefer one over the other. And in this context, these points that lie exactly on the margin, so exactly on these dashed lines, have a special name and they're called the support vectors. And this is why this whole approach is called support vector machines. And usually, if you see, these are very few. So most of the data points are outside of this margin, and only few data points are close to the decision boundary. How can we compute the distance to this margin? Or how can we compute the distance from the data points to the classifier, which is we just defined as the margin? Well, because we know that the normal, we can define the hyperplane via the normal unit vector. If you plug it into the formula for computing the distances between a point and a line, you get exactly this term out. And what is this term? Well, it's just as before, our function that defines the line, right? So just the linear function of our coefficients and the data points, plus we multiply by yi. And yi is the target, it's the label, so it's either 1 or -1. So essentially it gives us the distance to this margin, right? So if we're on the positive side, we multiply by 1, you just get the distance. If we're on the negative side, this thing is -1, but then yi is also -1. So again, we just get a positive number. So, okay, then how do we actually find this line? Well, we write down an optimization problem. We say, find these coefficients b such that the margin is maximized and it holds that bj squared equals to 1. So this just essentially ensures that the vector that defines the hyperplane is the unit norm. And essentially it's just a convention so that we can make sure that when we compute the margin, we can do it in an easy form. Then what it says is make sure that all of the data points are a distance greater than the margin, right? So if this is the distance, the signed distance, when we multiply by yi, we get rid of the sign. So essentially, for every data point, we have the distance, 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 and we want to make sure that all of these are bigger than this threshold m. And we want to make this threshold m, the margin, as large as possible. Does this make sense so far? Any questions on the definition of this margin-based classifier? So if we go back to our discussion of hyperplanes, so this is a hyperplane, the line, and normal vector is the vector which is perpendicular to this hyperplane. So in 1D, it's this vector that has 90-degree angle. In 2D, it's the vector that's perpendicular to it. In 3D and so on, it's the same idea. So essentially, you can define, there's an equivalence between this vector and this equation that defines the line. So as I rotate this vector, I get different hyperplanes. Yes, exactly. Further questions on maximum margin classifiers? So these coefficients are variables, and we're looking for the best possible variables such that this m is as large as possible and this constraint holds. And in general, this is called constraint optimization. And in this particular case, it's convex constraint optimization problem. How to do this? It's beyond this lecture, but essentially you can imagine that there's a library where you can take any convex optimization problem, write it in a certain canonical form, you plug it into the library, and then you get the optimal B0 to BP. Yes, so we know how to solve linear programs. Those are programs where the objective and constraints are linear. We also know how to solve convex problems where the objective and the constraints are convex, and there are also some generalizations. But for these sets of problems, there's a machinery, a set of tools where you can plug your problem in and you get the optimal solution out. And yes, essentially, there's lots of theory of why this works and how it works. But for the purposes of this lecture, or for the purposes of SVM, just know that there's a way to solve this problem and get these betas out. And they are really the best possible betas. So if you run, let's say, gradient descent on some problem, we might get a local minimum, but not the best minimum. But here, because the problem is convex, we will get the global, the best minimum. That's also a study. So there's convex optimization or convex analysis, and there's certain rules of how you can check convexity. So one thing is, for example, you can look at the Hessian, so the second derivative, and check its curvature. You can also know there's a certain set of primitives. Let's say you start with some convex functions that you know that are convex. Somebody has proved it. And there's rules of how to combine convex functions such that the result stays convex. For example, sum of two convex functions is always convex. So then if you have a problem and you know this primitives, you can see, can I show that this problem is built up out of these primitives? And that's also proof of convexity. Okay. So we can solve this problem, but what happens if our data set actually is not linearly separable, right? If, let's say I had a red data point here, then there is no line that will satisfy all of these constraints, right? So one of these constraints or more will be violated, and then there is no optimal solution. So what do we do then? Well, then we can do something which is called, so this is this example, right? So here, there is no line that can separate. Any potential line you draw has at least one misclassification, which means this problem is infeasible. We can do something, and we generalize from what is called the hard margin classifier to the soft margin classifier. And the soft margin classifier allows for some misclassifications. We'll see how that looks like in a minute. Another thing to consider here, that even though the data might be separable, looking for this best possible line while making sure that everything is correctly classified is not a good idea. And intuitively, you can see this from the, let's say, discussion on overfitting. It might be that my training data is noisy, so even if I can perfectly separate, maybe I don't want to, right? So here we have the solid line, which does make sure that everybody is correctly classified, but intuitively, this other dashed line gives us a better slack. It gives us a better margin to the blue points and the red points. Yes, to do that, we need to sacrifice one blue point, but maybe that's okay, because we expect that the dashed line will generalize better on some test data set. Or in other words, just what we've written on the slides, we have greater robustness to some small perturbations. We avoid fitting the noise. And both of these problems, so overfitting and if the data is not really separable, can be solved with this soft margin classifier. And what we do in the soft margin classifier is we define, again, a hyperplane, but now we have two kinds of special points. For one set of points, like these two, we call them misplaced. They're misplaced because they're still correct. So this is still on the blue side and this is still on the red side, but they're within the margin. So if you go back to this equation which says the equation of the hyperplane has to be bigger than m, this is bigger than 1 and this is bigger than -1, but it's not bigger than m. So it's still on the correct side, but just not bigger than the margin. We also have another set of points, like these two, which are really misclassified because they are on the wrong side of the margin. So essentially the sign of this data point and the sign of this data point are different from what they're supposed to be according to the training data. And when we do a soft margin classifier, we allow for both kinds of mistakes. This is how the problem looks like. So everything is the same as before, but now, in addition to the margin, we allow for a little bit of slack. So these additional variables, epsilon I, allow us to be wrong. So let's say we have these two data points, right? They're on the wrong side of the boundary. And let's say that the margin we've selected is 1, right? So we want, this is the 0 line, this is the -1 line, and this is the +1 line. What should the value of epsilon I be for these data points in order for this equation to be satisfied? Right? If we plug in the red data point, here we will get a negative number, right? Multiplied by a positive number, so the prediction does not match the class, we'll get a negative number. If m is 1, then we have 1 minus epsilon 1. So here we have a negative number, which is something less than -1. Let's say it's minus 0.5. This is 1 minus epsilon I. So what should we set epsilon I to in order to be, for this to be satisfied? Yes? Yes, for example, larger than 1 would work because then we would correct, essentially. So this would make sure that this side of the equation holds. What is here also a good idea is to set epsilon I to the smallest possible value. And the smallest possible value is exactly how far am I misclassified. So we see this is point number 11. It's supposed to be here or further. So this is by how much it's making a misclassification. So if we add that much slack, if we set epsilon I exactly to this value, then this equation will hold. Does that make sense? And what we additionally add here is a second constraint where we say the sum of these epsilon I values, so how much misclassification, how much violation we are allowing, should be less than some constant. And intuitively, this constant is our budget for misclassification. So the larger the constant, more points, we're going to allow more points to be misclassified, which means maybe we find a better and better margin, but there's a trade-off, right? If we allow all of the points to be misclassified, we don't have a good classifier in the end. Yes, so this is exactly what I said. So this is our budget for total misclassification, and these additional variables are called slack variables because essentially instead of fully satisfying the margin, we only partially satisfy it. And so again, this is another optimization problem. We can still plug it into the library and we'll get now solutions for the betas, and we'll also get solutions for this epsilon I. And because the best thing to do is to choose the smallest possible epsilon I, when we do this, we can interpret these values. So if epsilon I is 0, What does that mean? We're on the correct side of the margin. No need to add slack. If epsilon I is positive, then the observation is on the wrong side of the margin, but not completely misclassified. So it's still correct, but on the wrong side of the margin, right? Because if we are within this value, then epsilon I is between 0 and 1, essentially. And if epsilon I is also bigger than 1, then the observation is not only on the wrong side of the margin, but also on the wrong side of the hyperplane. And another thing which we can observe from this optimization problem is another way to interpret this parameter C is that C essentially sets the total amount of points which can be on the wrong side of the hyperplane. So let's look at a couple of examples of how this problem, what is the optimal decision boundary, what is the optimal max margin classifier for different values of C. So here we've allowed a very large value of C, and we see that this is our classifier and these are our margins. So now essentially everything is within the margin. Slightly smaller classifier, slightly smaller value of C, the margins essentially decrease because we allow for fewer misclassifications. Even smaller value of C, again, the margin gets smaller, but less points are misclassified. So if you look at here, let's go even to the first problem. We have 1, 2, 3, 4, 5 misclassified data points on the wrong side of the hyperplane. If we go here, there's 1 misclassified blue and 2 misclassified red. If we go here, we have 1 red and 1 blue misclassified. And then if we go even a smaller C, we see that 1 red is the same, 1 red, 1 blue misclassified. What you should take out of this is that C controls essentially the number of misclassification. It's a penalty on how much we are allowed to misplace nodes or observations. Yeah, here for completeness, we see all 4 cases, and you see how not only does the margin change, but also the actual hyperplane that we find. So here it starts in this orientation and then it rotates. And yeah, as we get smaller and smaller, we converge to some value. So what will happen if we set C to 0? Yes, and we just recover essentially the original hard margin SVM. Okay, so given that C has this behavior, how would you choose it in a practical problem? Yes, exactly. Good. Now we all know cross-validation is the answer to everything in machine learning. So yes, we choose a C via cross-validation. And before, right, we had that the data points which are exactly on the margin were the ones that were called support vectors. But here, because we also allow data points within the margin, those are also called support vectors. So here, essentially all data points that are on the margin or on the wrong side of the margin, all of them are called support vectors. And the interesting thing about these support vectors in both hard and soft margin SVM is that if I now change this data point that's far away from the decision boundary and definitely not on the margin, definitely not inside the margin, I can wiggle this data point however I want, rerun the problem, the solution will be the same. And this is true for all data points that are outside of the margins. Only the data points within the margins will change the solution. So what we can also say is that this parameter C controls the bias variance trade-off. So if I have a large number of C, so this is this case, I have many support vectors, right? I just said that all of the data points on or inside are the support vectors. Here, all of these are inside support vectors. And the smaller the C is, the fewer support vectors we have, the larger the C is, more support vectors we have. So large C, margin wide, many support vectors. So knowing this, would you say that a large C has low variance and high bias, or high variance and low bias? Yes. Okay. What is your intuition here? Yes, yes, that's one good way to think about it, right? So, or another way to think about it is in terms of this overfitting idea, right? High bias means that we might be wrong because we're not getting exactly the correct classifier that fits this particular instance of the data set. But low variance, which means that if we rerun the process many times, we'll probably get the same classifier. And that's exactly right. So low variance and potentially high bias, depending on how the data looks like. And the other way around, if we have a very small value of C, the margin is thin, but now we have very few support vectors, and now these few support vectors exactly control how this decision boundary looks like, which means we might be overfitting to them, which now means high variance. So if I resample the data set, exactly these data points will be might be different, which if they are different, this complete decision boundary might change. So we have high variance, but we have small bias because we have fitted our data much more precisely, including potentially the noise. Yes, I guess it's like on a high level, it's good to think of them in a similar manner. Yes, yeah, they control essentially the behavior of the function. They control the behavior of the model. And here it's an even more extreme case compared to leverage points, because these points, the points within the margin, only those control the classifier. All other points, whatever you do to them, will not change the classifier. Yes, and this is actually one of the beneficial properties of support vector machines that I guess you can see it both as a positive as a negative, but mostly it has positive connotations, as we'll see in a little bit. So what happens if I have nonlinear decision boundaries, right? So in this case, this is the true data set. As before, we have the blue and the red data points. But in this case, not only the data is not separable, but it doesn't even make sense to fit a line here to find a hyperplane. Because, I mean, here we can see it. An optimal or a good idea for a classifier would be something like a circle. Everything inside the circle is one class, and everything outside of it is a different class. Here, what we can do as a first option is the trick that we did in the Beyond Linearity lecture, right? So, or also in general, right? Whenever I have a linear model, I can still use it by taking my features and adding extending my feature set. So instead of just working with xi to xp, I add the xi squares. Maybe I also add interaction terms like x1, x2, x2, x3, and so on. So I enrich my data space, I enrich the set of features, and then I fit a linear model on top of it. Because a linear model on a larger feature set, if you project it down to the original P features, will be then nonlinear. And I think we saw that in the Beyond Linearity lecture. How does the optimization problem look like? Well, it's the same as before. Again, we're now maximizing over B0, B1, and so on. But because now we have added additional features, so we added the x2 squared, the x1 squared, xp squared, and so on, each of these gets their own coefficient. So before we had B0 plus all these terms that multiply directly xi. Now we've added additional set of terms that also multiply xi squared. But of course, you can add many more terms. What is important here to keep in mind, similar to the lecture on splines and so on, this model is still linear. It's still linear in the coefficients beta, which means this whole problem is convex, which again means we can plug it into a library and get the solution out. Right? Everything is the same. We still ensure the unit norm constraint. We still ensure the margin constraint. And we're done here. What we can do in support vector machines is something more clever, though. Because of the special way this classifier is constructed, we can use the so-called kernel trick. And this is a very efficient trick, and it's actually applicable beyond SVMs in many other domains. So it's important to understand what is happening here. So if you look at this optimization problem, you can rewrite it into a different form. And once you rewrite it, turns out that the classifier can be written as a function of the bias term plus some now new variables called alpha I, where the term multiplying alpha I is the inner product between our test point and our data points, our training data points. So let me say that differently, right? Before, our function f of x is just the function of a line. But here, when I want to predict what the prediction is for a new test example, I look at its inner product with all of the training examples. So I see essentially how similar is my new test point with training data point 1, 2, 3, and so on. I get these coefficients. I multiply these coefficients with some alpha I variables, and this thing is exactly the same. So it will give me the exactly same classification as the sign of this beta 0 and so on. So this is, yeah, this is some rewriting. The details are actually a little bit tedious, but trust me, you can do this transformation. And these alpha I parameters, you can express them in terms of the data. You can express them in terms of these beta coefficients. So they're just, once you have solved the original problem, there's a way to convert that optimal solution into these alpha I's, and everything stays the same. And what is even more interesting is if you look at this sum, so this sum goes over 1 to n. So I look at the similarity of the test point x star with all of the training data points. But actually, you can show that these alpha I coefficients are 0 for all of the non-support vectors. So all the points that are outside of the margin, when you plug in the optimal solution, they'll get an alpha I of 0. Which means now I can alternatively rewrite my classifier as beta 0 plus sum, again, the same thing, but now the sum is only over the set of support vectors. And this makes the fact that we mentioned before that only the support vectors control the function very explicit, because now here we do see it. So we know that this thing is equivalent to the sign of this thing. And we see that here only the support vectors change this function. So I take a test data point, I have a small set of support vectors, I compute the dot product with all of them, multiply it with these coefficients alpha, add the bias, and I'm done. Right? Which now means that this could also be very efficient because I don't need the entire training set. I only need the set of support vectors. And what is interesting is because now the classifier is entirely defined in terms of these inner products, we don't actually need to know the coordinates of the observations, right? We only need a way to measure how close is our test to some xi from the training set. We don't need to actually know what is the coordinates of the x and what are the coordinates of xi. Because to calculate these alpha I beta zeros, we only need all pairwise products. Let me say that a little bit differently. So the optimization problem where you search over B0, B1 to BP, and the optimization problem where you search over B0, alpha 1, alpha 2, and so on, these optimization problems are equivalent. So I can solve the first one, find the betas, convert to alphas, or the other way around, I can solve the alphas and convert back to the betas if I want, but you can also just use the alphas directly. In other words, there is a way to solve this problem, and the only input to this algorithm are these inner products. If you know the inner products for all potential n choose 2 pairs, meaning all pairs of training data points, then you know how to find the optimal function. You don't need to know the actual coordinates. And this is exactly what makes this approach really interesting, because now we can very easily generalize it. Instead of saying, I have just the linear inner product, where I just take xi, xj, multiply sum of xi dot xj, sum over all j, right? That's how this inner product is defined. I can have an arbitrary kernel function. So this is where the name kernel trick comes from. And kernels essentially tell us how similar are two data points. We had this linear kernel, and this kernel measures essentially the correlation, the Pearson's correlation between the data points. But we can also have any other kernel you can think of. So, for example, one popular choice is the polynomial kernel of degree d. So now the similarity between xi and xi prime is measured in terms of this function. Or we can also have the radial basis kernel. And here the radial basis kernel is e to the similarity, so the Euclidean distance scaled by some gamma. What does this remind you of? We've talked about something similar before. Right, this is the Gaussian, but where have we seen this kind of idea of measuring similarities and then putting them through a function to qualify the similarities? Yes. 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 Yeah, and TSNE, exactly. So all of these places use a similar idea where you're saying, okay, now instead of having my data point be linearly similar or measuring similarity in a linear manner to all other data points, I'm going to enforce some notion of locality, right? And here, essentially, for example, for the radial basis kernel, or sometimes it's called the RBF, for radial basis function kernel, this gamma essentially measures exactly how big our neighborhood is, just like in TSNE. So a smaller gamma means we're concentrated more, a larger gamma means we spread out our similarity more. And in general, a kernel is essentially any symmetric function which is positive definite. So any function that's positive definite and symmetric is a kernel. Which means that this function can be, there's really a lot of options that we can plug in here. So this idea or this term, positive definite, it's a technical term. You don't really have to know what it means. Essentially, it's it makes sure, let me see, it's on the slides. I don't know, I guess you can't see it. Just a second. Right, so positive definite means that this thing holds, that if I multiply my kernel, so my kernel for any two inputs, xi and xj, and any non-zero vector, so these are some coefficients, ci, cj, whenever I plug in any of these numbers, it's always positive. And this is essentially necessary to ensure that when we use a kernel and plug it into the optimization problem, it stays convex. So if the kernel doesn't satisfy positive definiteness, then the problem will no longer be convex. Okay, so how does this look like? So we have our input space as before. The standard linear kernel just finds the line that best separates the data points with largest possible margin, while if we now, instead of measuring similarity in terms of linear distances, we measure similarity in terms of the kernel, we get a decision boundary that is nonlinear. And in this case, because the data set looks the way it looks, this is the best possible max margin classifier. Okay, we'll see how we get to this case after the break. So now we have 15 minutes break until 5:15. Okay, we can continue. So where we stopped was we talked about these decision boundaries, right? We have the linear decision boundary with the normal kernel, the linear kernel. Using another kernel function, we get the nonlinear decision boundary. And a very important theorem essentially says what happens when I choose any kernel function is that this kernel is equivalent to, again, a linear dot product in some other space phi. So I have my normal space, I take dot products here. If I apply this other similarity function like the RBF or the polynomial kernel and measure dot products via, or measure, let's say, similarity via this function or this function, it's equivalent to going to some other space, which could be larger or lower dimensional, and doing linear stuff there. And yeah, this is how this looks like. So we go from this space, we transform it into some other space, and doing linear dot products in here, it's the same as computing the kernel in here. So yeah, this is a general theorem which says essentially any kernel function which is positive semi-definite can be equivalently represented in this form. Right, so essentially applying the kernel, we do a transformation in some other space phi and then do the dot product. So if you want to learn more, this is called the reproducing kernel Hilbert space, or RKHS. Here's a link to the Wikipedia article. But yeah, you don't need to know all the details. Essentially, just know that this other space exists. And this is more for, let's say, theoretical understanding of what's happening, because we don't really need to construct this space. But in some examples, we can look at how this space looks like just to understand what this kernel is doing, right? So in particular, if we choose the polynomial kernel with D2, so this is the polynomial kernel, and if it's degree 2, essentially we add up, we do the dot product, and then we square it, right? So there you can explicitly calculate what is this space. So we go from the space of 2 dimensions to the space of 6 dimensions. So we had x1 and x2. We apply this kernel, the polynomial kernel, and this is equivalent to moving to this new space with 6 dimensions, where the dimensions are these transformations. So we see we have the bias term 1, we have x1 and x2 squared, we have the square roots of the variables x1 and x2 only, and we have the interaction term. So in this case, doing a polynomial kernel is equivalent to just creating these 6 new columns in your data set and running the linear SVM. What is also interesting is that if you have the radial basis kernel, so this function with the exponent, you can show that this space, the new transformation phi, is actually infinite. So you can never actually compute this new vector, but you don't have to compute it, right? Because you can just plug in xi and xi prime and get the value. But this can be shown that it's equivalent to creating an infinite vector for xi, infinite vector for xi prime, and multiplying them. Yeah, the intuition for this, if you've heard about this, it's because you can rewrite this in terms of the Taylor decomposition. But if you don't know about this, don't worry, it's not that important. Okay, and just one more picture to give you, again, more intuition of what's happening. So this is our original space, our original data space. The classes, the blue class is not linearly separable from the red class, but you can imagine that we can go to a different space via the kernel function. And now, so we go in this case from 2D to 3D. And in this new space, the data is separable. So I can find this plane that cuts the data into below blue and above red. And going back from this space to this space, the resulting linear decision boundary will be circular. And that's exactly what's happening in this example as well. Is this clear, this idea of going to a different space? Yes. In principle, I think you can come up with kernel functions that reduce also the number of dimensions. So, for example, you can say the kernel between xi and xj, or xi prime, equals xi3 times xi prime 3. You just multiply the third dimension, and this is your kernel, right? I discard all of the other dimensions. So in principle, the kernel could go down or up. Most of the times, it blows up the dimension. There is a connection which essentially says that PCA also measures things linearly. You can do something which is called kernel PCA, where you basically apply the same kernel trick to PCA. So essentially, just as with SVM, which didn't have these dot products, we can rewrite it into a dot product form. You can do the same thing for PCA. And then once your entire optimization problem is only in terms of these inner products, you can switch from products to kernel, and then it still works. Yes. Okay, so let's look at this example with the radial basis kernel. We have our test data point, and we essentially measure, just as we discussed before, how far away it is from all of the other training data points, which is just the Euclidean distance. We take the Euclidean distance, we plug it into the kernel. If the distance is large, the kernel value will be small. If the distance is small, the kernel value, the similarity, will be large. So essentially, how much is the prediction for a data point X star, for a test data point influence, depends on this similarity, which is depending on the distance. And yeah, essentially, as we discussed before, we have this additional hyperparameter gamma, which controls the locality. So a larger gamma, decreasing gamma increases locality. I think I said that wrongly before. So decreasing gamma increases locality. And this is also something that came up in a discussion in the break. Kernels, or SVM with kernels, but also kernels in general, tend to be very sensitive to these hyperparameters. So if you choose a bunch of different values of gamma, there's usually only a few values of gamma that give you a good test error. So you always need to do cross-validation. And in this case, if you do cross-validation, you need to cross-validate on this gamma parameter and on the C parameter, which is the budget of misclassification. Okay, so how does that look like? Before if we use the linear kernel, we get this decision boundary, which does a terrible job, doesn't really classify the points correctly. And now if we apply the radial basis kernel, this is the decision boundary that we find. And here, as before, so here we denote the margin is also these two lines. And here the margin also has the same shape, essentially, as the decision boundary. And yet another advantage of kernels is, as I said before, you don't really need the actual data points. The only thing you need is this pairwise matrix of similarities. How similar is xi to xi prime for all potential training data points? So you don't need to go to this feature space, which is large or potentially infinite. You only need to be able to compute similarity. And this is really nice because now it means we can apply it to arbitrary observations. So let's say I work with graphs. So I have one graph, so a set of nodes and edges, and another graph, a set of nodes and edges. How would you do machine learning on graph data? It seems like it's not a number, right? It's some object such as graph. I can't just plug it into a regression or into the vanilla SVM, right? But let's say I can come up with a function where I take a graph and a second graph, and I say how similar are these two graphs to each other. If I have a function that measures similarity, I can use kernel SVM. Or any other object like strings or molecules or anything else that is not inherently a vector. As long as I have a way of measuring similarity between them, which might be some complicated procedure or something simple, doesn't matter. As long as I can measure a similarity between two things, I can run kernel SVM. And this makes it applicable to many things. And as I said before, for the question, right, we can also apply the kernel trick to PCA You can apply it also to the linear discriminant analysis that you learned in the beginning of the lecture, but also to many, many other things. So this is really an important trick to learn and to remember. Okay, let's look at one example where we've applied SVM to the heart disease data. You know this data set from the previous lectures. Again, we have 13 predictors. We're fitting a binary problem, a binary target, where essentially we try to predict whether the individual has heart disease or not. And yeah, we have around 200 training instances and 90 test instances. And what we look at here is now we compare it just to the traditional classification, to the LDA that we've learned before, and when we compare LDA and the linear SVM. What we see that if we consider the performance on the test data, and essentially here we look at a special kind of plot. So this is the plot where on the x-axis we show the true positive rate. So for all the instances that are true, how many of them we get correct. And this is the false positive rate for all the instances that are actually false, how many of them we get correct. So what is the, sorry, for all instances that are false, that are true, how many of them we classify as false? So now we see that on the training data set, both let me also add one additional thing, right? So in LDA and linear SVM, we'll get output some value. So let's focus on linear SVM for the moment. F of x, when we plug it into our function, will get some number, right? And then we need to decide whether we want to classify this instance as positive or negative. So think of this number as, let's say, we've scaled it and it's a value between 0 and 1. And a value of 0 means it's class -1, value of 1 means it's class 1. So usually you would choose a threshold of 50%. Everything that's below 50% goes to class 0. Everything that's above 50% goes to class 1. This is, let's say, the default setting. But nobody tells you that you have to choose 50%. So you can vary this threshold. You can set the threshold at 10%, 20, 50, and so on, and look at the performance for all of these potential thresholds. And if you do this, so if I try all potential thresholds, I get such a curve. And this is called the ROC, or the receiver operating curve. And this essentially shows you how well the algorithm or the model performs across all potential thresholds. And what is the best possible case here? The best possible case is that this curve goes as much to this corner as possible. So a curve that's going flat up and then all the way to the right is the best possible curve. So we try out all potential thresholds for SVM, all potential thresholds for LDA, and then we see that on the training data, they perform rather similarly. These two curves are quite close to each other. What happens on the test data? So on the test data, we see that SVM does a little bit better. Why does it do better? Because it finds essentially the max margin classifier. And this has a tendency to generalize better because we are not fitting exactly to the noise. Okay, what we also look at here, again, the same thing. We compare now only the SVM classifier. We compare it for 3 different values of this gamma parameter in the RBF kernel, which essentially controls the locality. And then we see that the smaller gamma is, the more local we are, the more we care about, the larger gamma is, the more local we are, which means we weigh only the closest data points when we consider distances. And essentially, larger means more local, which means more overfitting. So for larger values, we get a much better training performance. But of course, if we now go to the test set, we see this reversed, right? So this blue line, which had really good really good training performance, has now terrible test performance, or slightly worse test performance. But also we see here that in this case, none of these different hyperparameters can give us a good solution. Yeah, so this is exactly what's written on the slides, that yeah, having a very large value of gamma, we get a very local kernel which has high variance, which means it doesn't really perform that well on the test set. Yes. Yes. So you can think of this kind of true positive and false positive rate curve doesn't have to be probability. So think of arranging all of your outputs on, let's you have a single real number that's not a probability, but just kind of tells you the confidence. And in SVM, this is the margin, right? For every data point, I can compute the margin. How far away am I from the decision boundary, right? So you can take all of these numbers for the training data points or the test data points, put them in a sorted array, and then look for a threshold between them. Everything above a margin of 70 is class 1. Everything below is class 0, right? I mean, 70 is just an arbitrary number. It's not a realistic number. But this idea of putting everything above and below a threshold works with any number. And in SVM, this is the margin. And here it will be specifically the signed margin. So we have margin that's positive, which means I'm on the blue side and I'm far away or close to the blue side, and negative distance from the hyperplane. Maybe better would be to say it's not the margin, but the distance to the hyperplane. So the more positive I am, the more confident. The more negative, I'm also more confident, but for the other class. Yes. Mm-hmm. Yes, yes. So you could do that essentially, or in other way, there's even a simpler way to do it, right? Once you know the corresponding threshold, right now the normal SVM classifier looks at the sign, right? You compute the distance, plug it into the sign function, +1, -1. Now instead of plugging it into a sign, you just check bigger than this number or smaller than this number, right? And that's equivalent to moving this hyperplane in, like, if this is the hyperplane, I can move it up or down, essentially along this parallel axis. Yeah. What is also interesting is that the SVM can be rewritten in yet another form. So it's very flexible. This is the third form that we're seeing. And we can go from this constrained optimization problem to a different, now unconstrained optimization problem. And this problem looks like this. We have, again, the B coefficients, the B0 to BP coefficients. We have a penalty term, which penalizes the squares of Bj. And we have now a different interesting loss function. So what is this loss function? Well, this value is just so this is the distance to the margin. When you multiply it by this, you remove the sign. So it's just a positive number, which if it's high, I'm far away. If it's low, I'm close to the decision boundary. And it checks if I am within, if my distance to the decision boundary is less than 1, then the output of this will be that number, which means I will count, I will contribute to the loss. If the distance to the decision boundary is more than 1, then this number will be negative, which means this whole thing is going to be 0 and a negative number, which will be 0. So what does this function do? It takes data points that are outside, they're more than 1 away from the hyperplane, and says, okay, you are more than 1 away, I don't care about you, you don't contribute to the loss, I only focus on the ones that are inside within the margin. Right? So then essentially this is equivalent. And we're just finding again all of these hyperparameters such that our loss in this case is minimized. And we see that this thing looks very similar to regularized logistic regression that we talked about before. So it has this general form of having some loss plus lambda times some penalty function. And if you compare, so what is this penalty function? It's just the penalty that we used in ridge regression. But in ridge regression, we used a different loss. So in ridge regression, we use this particular loss. So in ridge regression, you again plug the input into the function, multiply it with the label, and then you do this transformation, log of 1 plus e to the minus this thing, so minus the distance, essentially. While in SVM, we use this different loss function, which is max of 0 and the same thing. So in both of those have this input, the distance, but they just do different things with the distance. So how do these two different things differ? So here's the first one. Here's the second one. We plot it. So on the x-axis is exactly this distance, right? And on the y-axis is, on one hand, the SVM loss, which is this black line, which is this thing. And on the other hand, the green line, which is the loss that you use in logistic regression. And we see that these two lines are actually quite similar to each other. So after all this hard work and after deriving SVM and all of these different properties of it, the actual classifiers that you use turn out to be very similar to logistic regression plus with ridge penalty, essentially. Logistic ridge regression. Yes, so in general, based on how these functions behave, what you can conclude is that the more separable the data is, then SVM will perform better. And the more overlap between the two different classes is, then logistic regression tends to do better. But this is just like a rule of thumb kind of thing. It's not, let's say, theoretically sound that this always has to be one or the other. And what we can also conclude is that this budget C that we had in the SVM, which controls how many misclassifications we have, is actually inversely proportional to 1 over lambda. So there's a correlation between the two. Still, what would you say is the big advantage of SVM that we couldn't do in logistic regression? Yes? Yes, so we can do the kernels, essentially. It's much easier to incorporate kernels here than in logistic ridge regression. Okay, so as we talked about briefly before, SVM doesn't really give us probability. We can look at these distances to the margin as a way of guiding confidence, but like these distances can have any number of units, right? It could be that the margin goes between 0 and 100 and 0 and minus 100, but it also could be 1,000. We don't know really a good scale for this margin. So sometimes to communicate with other stakeholders, it might be easier if we convert these distances to the margin to probabilities. How can we do this? Well, there's many different ways, but one way is to say, okay, the probability of the class equals to 1 is now this function, which is 1 over exp, where f of x is now the distance, times two numbers, a plus b. So this is just some general parameterized function. And this is essentially the function which takes any number and squishes it to be between 0 and 1. It's the logistic function. We've added two parameters. A scales the input. So if I have margin scores that are on a very large scale, I can just multiply them by a small number to squish them into a good range. And B adds bias. So if I think of, so if this is the logistic function, so here are numbers on the real line, I plug them into the function, I get numbers between 0 and 1. So if I multiply with A, it essentially squishes, it changes the scale, but the shape is still the same. And if I add or subtract b, I just move the location of this curve. So I might get something like this, but still low numbers get a low probability, high numbers get a high probability. But the shape is still like this. So how do we find these parameters a and b? We just essentially fit this function on our data set again. So we fitted first the SVM, we got the best SVM, which is this f of x. Now we refit a and b to get just on the training data, just like before. And if we do this, this is how the probabilities on one example will look like. So the probability of the positive class and the negative class. And this is exactly this sigmoid function that does the squishing. So here are on the x-axis are the margin value or the distance values. So you see all of these have a positive number. They're on the upside of the decision boundary. All of these have a negative number. Plug them into the logistic, you get 1 and 0. And if you see this, so these are the numbers that we've actually, these are probabilities that we fit. It's a pretty good fit, right? All of the data points fit nicely on this logistic curve. Okay, so far, we can only do binary classification. How would you do multi-class classification? Right, if you think to this constraint that we have, it says f of x times y of I has to be bigger than the margin. And y of I multiplies it by -1 and 1. So there's really no good way to make this now multi-class, right? Because it just controls positive, negative. Do you have any ideas of how to do multi-class? Yes, exactly. So this is a very general solution. Whenever we have, for whatever reason, we only have a thing that can do binary classification, but I have multi-class problem, I can do these transformations. So one transformation is exactly what you suggest. It's this one versus rest. So instead of training a single model, I train k different models. And for each of them, I say 0 is the first class, all the others are the second class. Then 1 is the first class, all of the others are the second class, and so on. How would you choose then? So now a test point comes in, I plug it into these k classifiers. What do I get? I get distances. How do I choose which of these distances wins? The simplest thing is just to take the maximum distance. The second option is to do essentially all pairwise classifiers. So I do 0 versus 1, 0 versus 2, 0 versus 3, 1 versus 2, 2 versus 3, and so on. Really all pairwise classifiers. And then I train them separately. I take a test point. Now I get n or k choose 2 potential values. How do I choose the best one? You can do majority vote. So the first classifier says 0. The second says 0. The third one says 1. Out of all of these potential options, choose the one, choose the highest. So if 0 is reported most often, I just choose 0. You can also do a weighted majority where you say, okay, the distance to the margin counts more. So if first classifier says 0 with a high distance and the other one has 5 with a low distance, I trust the first one more. What is also interesting is there's something called one class SVM, where now you get some data set, but you don't have labels. You don't know what is class 0 and class 1. And you can still fit something very similar to SVM, which now tells you for a new data point, am I similar to the ones that I've seen before? So it's kind of like an outlier detection. I have a data set. I know that all of these are good points that make sense. I fit a model on it. And now in production, when new test data points come in, I can check how well do they match, essentially. If it matches, then it's not an outlier. Otherwise, it doesn't. Okay. So all of this so far was for classification. We can also extend the idea of support vectors to regression. And just as before, we have a linear model. We do x transpose b plus beta 0. This is, again, just a line. And Now, the difference that we're doing to traditional regression is that we're adding this special loss function. And the special loss function is the so-called epsilon insensitive loss function. So I have my data points. This is the input, the feature. This is the output. Let's say this is one model that I fit. These are all the instances. And then around the model, I define this tube, which, similar to before to the classification, has epsilon threshold above it and minus epsilon threshold below it. So this is similar to the idea of the margin. And then when I'm computing the loss, before we were just doing linear, we were just doing least squares. So how much I'm predicting is the output, what is the actual output, take the brackets, square it. So now we say the loss is this special function where if I'm within the epsilon distance of the line, the loss is just 0. I don't count. When I'm outside of the line, I count linearly. So the distance is just, now it's not a square, but it's just linear. You just report the distance as the actual loss. Right? And this is very similar to this hinge formulation, where as soon as I'm within the margin, I count. When I'm outside of the margin, I don't count. This is similar, but it's now flipped. When I'm inside, I do not count. When I'm outside, I do count. Right? So we're not going to discuss more details on SVR, so support vector regression, but we'll just show how it looks like. And we see that if we do here support vector regression with the RBF, with the radial basis kernel, we get these kinds of results. So we see that, so just to tell you what the plot is doing, this is the fitted model, the red line. The green lines are these epsilon boundaries that we discussed. So in general, if we have a linear SVR, we have the tube. If we apply the kernel to it, you get a nonlinear boundary, just like in classification. So here, this is the nonlinear boundary. These are the epsilon. This is the nonlinear model. These are the epsilon nonlinear boundaries. And the blue points are the data points that we use to fit the model. So now, again, this is switched to classification. The points that are on the boundary or outside are the support vectors. For classification was on the boundary or inside. What do we see is that just as we discussed, everything that's inside, so I've added all these new data points inside, they don't change the model. The fit is still the same. And these data points that are on the outside, those are the ones that control the shape. So you see here, I've added these 3 data points, which from this function converted it to this function. So it pulled up, right? Because it wants to fit these data points. Yes. Okay, we have one question on chat, which is, does random forest perform, or ensemble methods in general, perform better than SVM for multiclass? Yes, so it depends, but for, let's say, tabular data, which is most of the data that we considered in this lecture, where you have columns, which are features, and rows, which are examples, random forest will perform out of the box better than SVM, which means that the range of hyperparameters that you have that work well is larger compared to the range of hyperparameters for SVM. So SVM, you have to be careful when you tune the C hyperparameter or the gamma hyperparameter or the RBF kernel. There's very few values that work well. But for random forests and decision trees in general, usually if you just apply them out of the box, they more or less work. You can still do cross-validation. We can still find an even better model, but they tend to work more easily or better. All right, so that was the question from chat. All right, we're almost to the end. So today we discussed support vector machines, where the main idea is find a classifier that has some margin around it, such that you're not really overfitting to the data points, but you're ensuring that the data points within the margin all the data points are sufficiently far away from the margin. So we want, out of all potential hyperplanes, we want to find a hyperplane that has the maximum margin. And we started with the hard SVM, where we really enforced that all data points must be correctly classified. All of them must be above or below the margin. This works, but only if the data set is linearly separable. If it's not, we can't actually solve this problem. Also, we might not want to solve this problem in order to not overfit. So then we introduced this idea of soft support vector machines, where we now allowed some slack. We allowed some data points to be within the margin or even on the wrong side of the boundary. And we controlled how many of these violations we allow with this budget parameter C. What we also saw is that we can rewrite SVM in terms of inner products only. So, which means we don't need to know any coordinates. We don't need to know vectors that represent our data points. As long as we have a kernel which tells us how similar is xi to xj, we can apply SVMs. And yeah, this kernel trick is very important and can be applied on many other models. And finally, we also saw that linear SVM is also equivalent to logistic ridge regression, but the only difference is that instead of using the logistic loss, we use the hinge loss, which when plotted next to each other actually looked very similar. All right, do you have any questions on SVMs? Yes. Can you say that again? Mm-hmm. I see, for categorical features, yes. Then we can essentially do the same transformation as we did in the logistic regression. So we do this like dummy variable, for example, encoding. Yeah. That's another downside of SVMs, that decision trees can handle much better. Yeah. Any other questions? Yes? Usually, yes, I would say. Although, I mean, the nature of, let's say, machine learning or data science workflows is that you have a task that you want to solve, and you have a certain time, right? And then you just, usually you try a bunch of models with a bunch of parameters and then choose the one that performs best. So I don't know, maybe you are familiar with Kaggle, which is, let's say, a competition framework where people post a problem. I don't know, I want to predict the cancer of these cells or something. And then everybody else can compete to create the best possible model. So there's the training set, there's a validation set, which measures your performance. And then there's also a held out set, which nobody has seen until the competition is finished. So what people do, essentially most often, the winning solution is some sort of ensemble of many different, you train a bunch of decision trees, bunch of neural networks, some SVMs, you combine all of these outputs into one model, and this usually performs the best. Of course, it's not elegant, right? Because it's just like a hodgepodge of a bunch of different models. But if you only care about predicting as accurately as possible, then this is the best solution. But you should be careful. Accuracy is not always the best idea. And we'll see this in the very last lecture, where we discussed other important factors like fairness, privacy, and robustness. And when you do this kind of crazy combination of many models, then you cannot say anything about, let's say, the fairness of the classifier. And yeah, we'll see more in 2 lectures. We'll talk about that. Yes, so that's also, sometimes you can fit a second model, let's say a second linear model that takes in all the predictions from all these ensembles. So let's say the predictions are just probabilities. So it takes all of these probabilities, this defines a new feature vector, and then you just fit a model on top of it. So that's usually one of the techniques that works quite well. But you can also just like average them. You can average them based on the weight to some, let's say, to some another held out set, which tells you, okay, how accurate I am, like an estimate of the accuracy. The more accurate I am, the higher weight I get, and so on. There's lots of, let's say, creative choices here that you can do. As long as this set is not touching the actual final test set, and you do everything you do in a proper cross-validation loop, then you won't have any leakage. Yeah. Mm-hmm. I guess it's not a bad strategy, yes. So, or you can also try to focus on different parts of the data. So it could be that this one classifier does really well on the one subset of the data points, but terrible on another subset of the data points. So it has high bias within this part of the space, but low, high variance in this other part of the space. So then you can, yeah, train this one, train another one which has the opposite behavior, and then combine them. But yeah, it highly depends on the problem, and yeah, it's not, let's say, a real science of how to combine these ensembles. It's more like people trying out things and see. Essentially, the only thing that matters in this case is how good am I doing on the test set. Yeah. Yes, exactly. So there's this, I think you're referring to this multiple hypothesis testing problem, that if I have a data set and I try to, let's say, test, are the two means of these two distributions the same or not? And the more times I try, the more times I touch the same data set, the more chances I have to get a p-value less than the threshold just on accident, just from random chance. And yeah, you should correct for this. But yeah, in machine learning, people don't really follow these practices necessarily. Yeah. Yes. I mean, there was a very interesting paper. So one of the big data sets is called ImageNet, where you have a fixed train set, fixed validation, which you can take out of the train set, and a fixed test set. So nobody really does this idea of cross-validation, right? And even if you do it properly, right, I create one method, I optimize my method on the training set, I look at the test error, and then I'm done, right? But then I develop a new method in the future. Now, all of the knowledge I've learned from the first method, the information from the test set has leaked, right? Because I've looked at the test set. But I don't have a new test set. There's a single test set. This is how these models are, or these benchmarks are set up. So essentially, information from the test set leaks over time. As people develop new models, they cite each other, they get more intuition of how ImageNet and this benchmark works. Information from the test set leaks. So what one interesting paper did is they said, okay, we're gonna go back to the procedure of the people who created this data set, follow the exact same procedure, and create a new test set that has not been seen before. And of course, if this is, let's say, the x-axis is time, and this is, let's say, accuracy, and we have, I don't know, some neural networks, some better neural networks, some fancier model, some transformer model, even fancier model, the accuracy tends to go up. People come up with better and better models to fit this data set. And this is on this fixed test set that everybody knows about. So you can even cheat, right? You can look at the test set and just make sure that you predict exactly what's in there. So what happened now on the new test set that hasn't been seen before, surprisingly, is, well, first of all, what's not surprising, all of these models were way lower. So our estimates on this test set was highly, was very hopeful, right? Our estimate of the error was much better than it actually is. And this makes sense because as you're training a model, you're touching the test set, you're looking at stuff. So of course you have a higher error than the actual, lower error than the actual, no, sorry, higher error than the actual error you estimated. What was surprising, at least for me, is yes, all of the errors were low, all of the accuracies were lower, but the shape of this curve was same. So the models that are better, so like these transformer models and the fancier models, are also better in this new world where we have a new test set. So apparently there was some leakage, but the leakage was not terrible. And it depends, because ImageNet is such a huge data set. It has so many data points. It's difficult to actually really, really overfit. If you have a tiny data set with just 100 data points, I think the situation will look a bit different. Yeah. Then leakage becomes much more important. Yes, yes. Yes. So yeah, the theorem says that there always exists such a space where this similarity, complex similarity function can be reduced to just a normal dot product in this higher space. Sometimes we know how this space looks like in the polynomial kernel example, we could go from 2 to 6, and we can exactly write what the 6 dimensions look like. In the RBF kernel, we know also how this space looks like. It's infinite, but in principle, if you want, you can write down the first, second, third, and so on. Every dimension, we know its form. But also there are kernels for which we don't know. We know that such a space exists, but we haven't been able to derive what this space exactly specifically looks like. But yeah, the only thing that's important is that this space exists. Yeah. All right. Any other questions? Yes? The one class SD. Yes. How does it fare against? I think, yeah, that's more like an older approach. More modern approaches from today usually do better. But anomaly detection is an unsupervised problem, which makes it, again, very tricky because, yeah, there's no good way of measuring how good you're doing, right? So let's say if I have in class within distribution points and then some specific type of out of distribution, I can fool myself that I'm doing well because I'm doing well. I can reject this out of distribution points. But if it's a different kind of out of distribution points, I might perform poorly. And because the set of things that are out of distribution is essentially infinite, right? You can't really characterize it. It can be tricky. So you have to have some assumptions of what counts as in versus out distribution. And then depending on the assumptions, linear as one class SVM versus something else might work better. Of people would, yes, exactly, yes. Thank you. Yes. All right, thank you, everybody. See you next week.